Hello. All right. Today, let's talk spectroscopy, right? We're going to do the rovibrational spectrum of a diatomic molecule. That diatomic molecule is HCl. That's the one we're going to talk about, right? So we took some data. Let's get that data into Igor, right? So you have the waves available. Let's load general text. And I'm going to go right to that high resolution spectrum so that we can talk about that. What do we have? We've got two columns. The first column is the wave number. So let's call that wave number. And then the second column is the percent T. I'm just going to call that T. All right, I'll match that in number. I'm going to say over right here because I've already loaded this once, but I want to show it to you again, right? So we'll load that up. Good. Now we're going to graph that. So we'll go to new graph in the Windows menu, and we're going to do the percent transmission versus the wave number corresponding to that for this whole high resolution spectrum. Let's expand that puppy out so that we can take a look at it. All right. There we go. What do we see? We see a couple of things. One, something I'd like you to notice about the Omnic software, sometimes it pads out the numbers with garbage. Don't use it. Just because there are numbers there that came from a computer doesn't mean you have to use it. If you see something unphysical like this, you know it wasn't there. We only took data from 600 to 4,000, so this is garbage. So we definitely wouldn't want that, right? We'd want to start at 600 because that's where we really went, and 4,000 is plenty fine for us. Now, another thing that happens actually, right, is that right now we've got the low energy side down here and the high energy side up there, but we actually normally get it the other way around, right? Uh, when we do, I'll just auto scale that. We normally go the other way around when the spectroscopic notation is have the low energy red side over here and the high energy blue side over there. And in order to do that, what we'd have to do here is reverse the bottom axis. If we reverse the bottom axis, that's the way it was actually printed out on with the Omnic software, right? And now we can come in here and we change that to 4,000, that's fine. And then 600 down here, let's say, that's the useful range. Don't show that garbage stuff that came out at the end. All right, what's in here? There are a few different amalgamations, little, peaks that are joined together. And some of these have some real patterns to them. This is just something out of the optics there. But we've got things with real patterns to them, right? So we've got one way down here at low wave number. Let's expand that out. Bunch of peaks here. Move that down just a little bit there. Bunch of peaks here, and then some sharp thing, and then a bunch of peaks. This is I'm going to call this a branch of peaks over here, and a branch there, and a branch there. Interesting. Are they all like that? No, I've got some lines here. And these lines don't seem to have much of a pattern to them, right? There are lots of little, we're talking some really small lines here, and they're just, I don't see much of a pattern here. Whereas if we look at this section, pattern's pretty obvious, right? There's a branch here. There's like it's missing something in the middle, and then another branch over here. There's something maybe repeating down there. Kind of interesting how we're seeing these patterns. Pattern recognition. Whenever you see a pattern in nature, nature is trying to tell you something. There is information in patterns. This is actually the HCl spectrum. And again, a branch here, something missing in the middle. It's almost like a mirror plane, right? And then there's another branch, lines going up and down. Oh, it doublets. Wonder where that's from. Okay. And then again, if we go out here, some very small impurity peaks, right? Oh, wait a second. There's some very regular stuff. And then more very regular stuff, branch, maybe missing thing, another one, and these irregular lines. So what's this all coming from? Well, we had a couple of molecules that we were trying to get rid of, right? We didn't get rid of all of the water and CO2, all right? And they're both triatomic molecules, all right? CO2 is a linear triatomic molecule, and H2O is bent, right? Oh yeah, and then really you can immediately see that in the spectroscopy. And the nature of these water lines, that they're much more irregular and not nearly as regular as the CO2 lines, that comes back to that structure, the difference between a linear and a bent molecule. And then we have to explain, why does this one have something in the center, whereas this CO2 vibration, and maybe the couple that we had up here, and this HCl, which is another linear molecule, because of course the diatomic is always linear, it also has that structure of a branch, a missing bit, and another branch, a group of lines that sort of seem to act the same way. And up here, these are a mixture of CO2 and H2O lines, right? Some hydrocarbons might be able to absorb way up here as well, but that's pretty high. Okay, so we know how we model a vibration, right? We model a vibration through the harmonic oscillator, and we know what that structure looks like, right? It should be evenly spaced. We got a vibrational quantum number, 0 point energy. We start off at V equals 0, and then they go up equally spaced. And harmonicity means they won't be exactly equally spaced, and we don't have exactly a parabolic well, but we start off with the harmonic oscillator as our basic idea. And the harmonic oscillator, right? Almost everything's going to be in the ground state because we're at room temperature here. But where can vibrational transitions go? And they can go by changing the vibrational quantum number plus or minus 1. That's going to be in a harmonic oscillator. That's the only transitions we get. And since most of the molecules are in V equals 0 to start with, then they're going to go to V equals 1. That's going to be the strongest transition that we're going to see. However, at the same time we change the vibrational energy, we also change the rotational energy. And we know what our rotational model is. Our rotational model is that we've got a rigid rotor, and the rigid rotor has an energy that changes as J times J plus 1. That should sound familiar after today's PChem lecture, right? Okay, so the rotational energy related to the rotational quantum number J by this J times J plus 1 term. And then it's also related to the moment of inertia, I, or the rotational constant, right? The moment of inertia directly related to the mass through the reduced mass here, and directly related to R, the internuclear distance. Two very important topics right there. Okay, so we want to determine this rotational constant. We want to determine this fundamental wave number nu E. All right, nu E hat. Okay, how are we going to do that? Well, we need to know more about the energy level structure and about selection rules, right? We know what the selection rule is for the vibrational quantum number, all right, plus or minus 1. What about for the rotational quantum number? Well, the photon has an angular momentum of 1. The rotational state has an angular momentum that's determined by the value of J. When we absorb a photon, we have to conserve angular momentum. If the angular momentum of the photon is 1, then we're going to have to change the angular momentum by plus or minus 1 when we change the rotational state. This will be the case, especially if there is no angular momentum associated with the vibration. That's usually the case, but not always. And if there's no angular momentum associated with the electronic state. For all the molecules we're looking at today, that's the case. They have a sigma ground state, no angular momentum in that ground state. But, oh, wait a minute. Yes, indeed. What we see is that most of these vibrations, like this one in CO2, right? Maybe one of these is due to J plus 1 and one due to J minus 1. Delta J, right? It has to change. And then maybe what was going on here is that we actually had delta J equals plus 1, delta J equals minus 1, and delta J equals 0. And indeed, that's what we're going to find out. This is a Q branch. This is a P branch. This is an R branch. Why do we go Q, P, R? Low energy side. Oh, the alphabet, P, Q, R. That's where the naming is going to come from. Let's see why those happen. All right. Let's take that diagram again, expand it up. Let's take a look at what we got here, right? The ground vibrational state is V equals 0. The first excited state is V equals 1. To differentiate the ground state from the excited state, we're going to put double primes on the ground state and primes on the upper state quantum numbers. All right. So we could start off in some level, right? A rho vibrational level. We know that it's going to be V equals 0, and there are various rotational states that are populated initially just by thermal excitations, right? Because this spacing is much smaller than the spacing between vibrational states. So let's say we started off in J equals 4. There are 3 possibilities. We could go delta J equals -1. We could go delta J equals 0. We could go delta J equals +1. The longer the arrow, the higher the energy of the photon that connects the two, right? And in HCl, there's no angular momentum associated with the vibration. So we're not allowed to do the Q branch. We're not allowed to do delta J equals 0, but we could do delta J equals -1. So if we started in 4, we end in 3. Or we could do delta J +1. If we start in 4, we end in 5. All right. The shorter arrows are going to correspond to the low energy side, the P branch. The longer arrows, the high energy side, the R branch. Let's go back to the spectrum. This is the HCl region. This is the CO2 region. This is actually a stretch from CO2. It has the same P, no Q, R structure. This is a bend, and that bend, it's doubly degenerate, and it does actually have angular momentum associated, and therefore the Q branch is allowed. Let's take a look at the HCl region. The HCl region, ooh, is very interesting, right? Okay, we've loaded this in. Wait a second, let's make this look like a real spectrum, okay? Name the axes, right? The axis label. Right, let's put the wave number on the bottom and the appropriate units on the left-hand side. That's %T. Stick those in there. Great. You know what? And we're going to, do I want it to go all the way to 0? I don't want it to go all the way to 0, right? What I would like to see is something that, you know, goes to 4,000. That's fine. Starts at 600. And, right, I don't need this to go to 0. That's from that fake data out here. I don't care about that, right? I want to have these peaks as big as possible. So let's make this have a minimum of 40, right? Let's just give that a rational number. Let's make it 101, right? Maybe 2 just for a little more space up there. And that way, when we put the mirror axis in there on these 2 to make it look a little more official, right? We've got a real nice spectrum, right, that corresponds to the area, and our peaks are nice and big and we can see them. Good, right? I'm gonna, you know, you're gonna do a whole bunch of peaks or a whole bunch of plots of spectra that all have to have wave number on the bottom, all have to have %T over here. They're gonna have different ranges, and so we're gonna have to change the range. But everything else, wait a second, I'd like to use this as a template. To use it as a template, click on the red, and I can save this as a recreation macro. Let me call this the full underscore spectrum, right? Save it, and then that way I can just go up here to the Windows and find the graph macro full spectrum. Boom, open it up. And if I wanted to add some new waves to this, right, I don't have to start all over again and do all that labeling. I can just append, right? If I wanted to do T1 versus wave number 1 and put it in here, bam, there it is. And then I could remove the old one that I didn't want anymore. And I could then, oh, wait a second, I'm going to have to change the axis and things like this. But at least my labeling, right? My labeling is all here the way it should be. If I don't want that after all, I can always say no save, and then I won't mess it up. All right, let's look again at that full spectrum. Okay, good. We've got something that looks much more useful. What about this HCl region? What's going on here? We'll expand that puppy out. Okay, yes. Oh, wait a second. So here's where the Q branch was. The P branch is on the low energy side. The R branch is on the high energy side, which corresponds to what we expect, right? The low energy side is the P branch. The high energy side is the R branch. Oh, wait a second. R branch transitions, if we started in V equals 0, the first transition, the one at the highest, the first transition, right? Because we're always going boom, and then we'll start here and we'll go to that one. Oh, wait, where's the first one? The first one starts at 0, and then it should go to J double prime equal 1. And the second one should start at 1 and end on 2. The next one should start at 3 and end on 4. Oh, okay. Whereas the P branch, if it started in J equals 0, it'd have to go to -1. That doesn't exist. So the first P branch line starts at J equals 1 and goes to 0. Oh, now look at the structure we have here. The first R branch line starts in J equals 0 and ends in J equals 2. This one starts in J equals 1 and ends in 2. Oh, now we know the quantum numbers associated with each and every one of these. We can assign these. This starts in J equals 0, J equals 1, J equals 2, J equals 3, and so on out. Whereas the P branch, the first line starts with J equals 1. J equals 1, 2, 3, 4. Now we know the pattern. We know exactly what all these lines are. R branch starts at J equals 0. P branch starts at J equals 1. And now we can read off the wave number of each one of these and how of each one of these transitions. How do we do that, right? Well, of course, we can go in there and grab tool. Oops, not the tools. Tools are for graphing tools, right? We want info. We can grab a cursor, put it on here, and we can move it around with the arrow keys, find out where the peak is, read off the wave number of that peak, right? Oh, wait a second. Is that good enough? What we want to do then is actually make a table 10226, and there is the peak wave number. All right, the peak wave number. We jot that down. And which peak is that? All right, that's the first transition in the P branch. It starts at J equals 1. Remember, P branch starts in J equals 1, and the R branch starts in J equals 0. So now we know that. And then we can go through each one of these and get the peak wavelength value, right? Get it out there. Don't just take it to the wave number. You want at least 2 decimal places. 3 is really getting crazy. You need it to at least 2 decimal places. But hey, if you got the third one, why not take the third one, right? Oh, wait a second. There's something else crazy about this. Look at this. We got 2 peaks here in like a doublet. Why are there 2 peaks close together? Looks even better when we expand that out a little. 2 peaks close together, and the one peak is about 3 times bigger than the other. And you can see that throughout this range, right, for the HCl lines, they all are like that. But that's not the case over here. So that's not something to do with the P and Q and R branches. It has something to do with HCl. What is that aspect of HCl that is causing a doublet of these two in a constant ratio of about 3 to 1? The answer to that can be found here, right? The rotational constant depends on the internuclear distance, the bond length. That's the same for all HCl molecules in the vehicle zero state and a particular rotational state, right? But, oh, the reduced mass. The reduced mass goes into determining the rotational constant. And Cl is kind of interesting, right? It has what, 34 and a half as its, atomic mass, because there are two well-populated isotopes in about a 3-to-1 ratio. All right, so that's where this is coming from. One is the more abundant isotope, right? The Cl35, and the other one is the Cl37, the less abundant isotope. So you can tell the difference between these two isotopes of HCl, and that's what's causing this doublet structure, right? The two closely spaced peaks, different isotopes. All right, so what we're going to do when we look at the, and in order to get the frequencies, we're going to concentrate on the big peaks, right? And we won't worry about the small peaks. We don't have to pick those, but we do want to go out here and pick as far as we can, right? Even if we can get some little peaks out here, because the more peaks we get, the better it is. So we're going to take the big peak, the big peak, the big peak. Oh, maybe, right? Kind of hard to tell. This one, definitely, there's a little one, there's the big one, then we're just kind of running out of space. What about the other side, right? Well, and if we had had more pressure or even went longer in time, you pick up, because the signal to noise is pretty low down here, right? There's the big peak, the big peak, the big peak. Probably that's the next one, but it's starting to, we're worried about it, okay? Definitely these three, no problem whatsoever. We would have had to go to even more pressure and to maybe even longer averaging. Remember, we changed it. We went from 600 to 4,000 inverse centimeters and 128 scans to get this. If we'd gone to 256, we might have flattened that out enough to really be able to determine whether that's the next peak in the HCl spectrum. Okay, so now we understand what's going on. We've got a P branch, we've got an R branch, and we've got isotopes, all of those effects playing a role, and we know how to explain that. Now what we want to do, right, is determine this rotational constant and this fundamental wave number. All right, how are we going to do that? We need some spectroscopy, and let's keep in mind that the rotational constant depends on R, and R changes with the vibrational quantum number, because see how we have that little bit of anharmonicity here? The molecule gets longer when we put it into V equals 1. All right, so now what we want to do is express the energies of the states, not in joules, but in inverse centimeters. And then we call that the term. That's what this is. This is the rovibrational term. It's the vibrational energy plus the rotational energy expressed in inverse centimeters. And that way we can get the wave number of a transition. It'll just be the energy difference between the two states involved in the transition. And if we have expressions for those, then we can calculate what the frequency of each transition is. We know how to get the frequency of each transition. We read it off from the big peak between the doublets, right? And we get that, and we make a list of J, the state it started in, right? And the frequency, all right? The wave number of each peak, all right? Now we want to determine the rotational constant. There's going to be a rotational constant for V equals 0. And because the bond length stretches in V equals 1, there'll be a different rotational constant for V equals 1. So we want to determine both of those, and we also want to determine this fundamental wave number. All right, the way we're going to do that is by using what's known as combination differences. All right, let me show you the second one here first. Let's take all the transitions that begin in the same value of J. We're going to take the wave number of an R branch transition that begins in the level J. The rotational quantum number is J. We know that V equals 0 to start with for all of these, right? And we know that it ends in V equals 1. Don't worry about that. So let's just say the R branch transition that begins in state J, and we're going to subtract from that the wave number of the P branch transition that begins in the same J state. We can substitute in from the rigid rotor, harmonic oscillator, rigid rotor, the energy of both of those that we, or the wave number that we expect for those two transitions. And we're going to subtract those. Oh, the fundamental wave number will cancel out. That's good. We'll determine that later, right? And we have the frequency that we expected for the R branch transition, because it starts in this J and goes to J plus 1 state, right? And we're going to subtract off from that the wave number of the P branch transition that started in the same level. So imagine this. This is actually one time it's easy to do something in Excel. You make one column that is the value of J. You make another column that is the value of the R branch transitions for that value of J. And you make another column that is the P branch transitions for that as a function of J, right? And you just subtract those two columns from each other. That is what this calculation corresponds to. And if we do the algebra here, that combination difference should be equal to 4 times the rotational constant of the upper state, right? Because the lower state one, this one canceled out with that one. So we only have the upper state rotational constant. We're going to plot this as a function of J plus 1. The J is the value of the state it started in, right? And we should get a straight line with the slope 4 times the rotational constant in the V equals 1 state. Perfect. That's really easy. And if we know the frequency of the P branch transition that started in 1, we can actually solve this equation back here for what we know what the frequency is. We can solve that. We can use that to solve for the fundamental wavelength. Oh, we need the rotational constant, though, in the ground state, the V equals 0 state, to do that. How do we do that? We need another combination difference. And this time we're going to do a combination difference that all of the transitions end in the same state. Oh, wait a second. All right. We know what they started in. We've assigned the spectrum. Now we can figure out how to get them to end in the same state. So if we take the value of J, right, our transitions all go up by 1. P all go down by 1. If we need them to end in the same one, we have to take the R branch transition that's 1 below our J value, the P branch transition that's 1 above the J value, and we can get them to end in the same value of J. Subtract those two. How do we do this? I did program in Igor to do it. If you want to use Excel, you can do this. What you have to do is move, right? You have those two columns, copy them into of all the frequencies, right? Copy them, move them over. One you're going to move down, one you're going to move up, and then you can subtract the two from each other. Think about it in terms of an Excel spreadsheet, and you can get it to work pretty easily. This is the one place where a spreadsheet really works easily. You take that combination difference of all the wave numbers of R branch transitions, subtracting off P branch transitions that end in the same value of J. Again, substitute in from the expression we had for the wave number of a transition, and you get that this second combination difference, when plotted against J plus a half, will again be a straight line, but this time 4 times the value of the rotational constant in the V equals 0 state. All right, so that's what you need to do for the calculations. Once you have both B0 and B1, you can use any transition. Here I've just done it for the P1 line, but you can do it for any transition to figure out what RE is. And then you can also go back and determine the equilibrium bond distance in the V equals 0 and V equals 1 states from the value of B that you've got. It'll be slightly different in those two states because you have slightly different values of RE, the equilibrium bond distance. All right. Okay, so all of that you're going to determine from these spectra. So everything else should be just like what it says in the manual here. You're going to make a bunch of plots. You're going to see what changing the resolution did. You're going to make another plot showing what happened when you increased your signal to noise by increasing the number of spectra collected, right? And then you're going to do that full analysis. The only spectrum you have to determine the actual wave number of the frequencies is for this high resolution spectrum. Find as many as you can, right? And remember that the biggest peaks here, this is the HCl region. This was CO2, right? So it's this region of the spectrum that you're going to want to concentrate on. Find as many peaks as you can, right? That you're sure correspond to that intensity pattern, right? There's a degeneracy and a Boltzmann factor, and that's what leads to this going up and down in intensity through those. All right. Go back there and you're going to determine all of those spectroscopic constants as well as the force constant, the effective nuclear internuclear distance. Compare the ground state values to literature. You might be able to find them here. You can also find them in the NIST web book. Great source of information there for the spectroscopy of diatomic molecules.